Okay, Spiderman uses his spider webs to save a runaway train moving about 60 kilometers per hour. His web stretches a few city blocks, 500 meters, before the 10 to the 4th kilogram train, which is 10,000 kilograms, comes to a stop. Assuming his web acts like a spring, estimate the effective spring constant. So let's pull out the information that we have. So we have VI, and we'll highlight it first. So key information. Okay, so our VI is 60 kilometers per hour. Our displacement from what we're assuming is the equilibrium position, right, where it's not stretching and now it is stretching, is 500 meters. The mass of the train is 10 to the 4th kilograms, or 10,000 kilograms. We know that it's going to come to a stop, so we know the final velocity is 0, and we're looking for the spring constant. So using what you have, now we've done spring constants with vertical, so looking at the change in potential energy. So that is a bit perhaps easier to think about, but now we've got a velocity that we're dealing with and trying to figure that out. The first thing that I would consider doing is changing your units over to something that is acceptable for our standard units, and that's going to be meters per second. So we're going to say kilometer to meter, 1,000 to 1, and then hour to second. So 3,600 seconds in an hour. So kilometer, hour, and that's going to give us roughly 16.67 meters per second. Now try to carry as many of those numbers, so it's really just 0.666666 on, and so try to carry as many numbers as you possibly can when you are finalizing that. So we're looking at the work done by the spring, which is his webbing, is going to be equivalent to the change in KE. So you can think about, we've talked about what work is equivalent to, and again, we're thinking about an elastic potential energy. So we can sub this out to say 1/2 kx squared, right? Because the work done by the spring, which again we're assuming that his spider web is acting like a spring, is going to be 1/2 kx squared, just like we did in the lab. Now remember that springs always do negative work, so that's an important thing to remember. So I'm going to put a negative sign there. Is equal to the change in kinetic energy, so kinetic energy final minus kinetic energy initial. Now our final kinetic energy is 0, so it's going to be minus 1/2 mvi squared is equal to negative 1/2 kx squared. Now we've said before that the spring constant is always positive. Remember that the spring constant is sort of a measure of the elasticity of the spring or rubber band or whatever the elastic material is, and that it's constant for that particular substance. So we can see that we have a negative on this side and negative on this side, and those are going to cancel. And also you could probably see that our halves are going to cancel because they're on both sides. So our negatives will cancel, our half will cancel, and that's going to leave kx squared equals mvi squared. We're looking for k, so we're going to get rid of x squared on that side, and that's going to leave us with k equals mvi squared over x squared. Now this is extremely manageable at this point. All we're doing now is plugging in. Conceptually, you have to understand why you're using this particular equation to figure it out. You can't force this information into another type of scenario or another type of equation. So now we can plug in. So we have our mass is 10 to the 4th kilograms. So we can say 10 to the 4th kilograms times 16.67 meters per second. That's squared over 500 meters. And all of that is squared. I put parentheses around this because if I put it just on the meter, then it only looks like it's meter squared. If I put it on the outside of the parentheses, it distributes to both the 500 and to the meter. Okay, so that's an important thing to note. All right, so when I do this, I get K equals 2,778,889 newtons divided by 250,000 meters. Newton over meter is our unit for K. When I divide that out, I have a positive 11.12 Newton over meters, and that is what the spring constant of Spiderman's web would be in order for this scenario to be valid.